Hey, it's Rob here with Sine Wave Specialties all over again, and we are back from the holidays. And it's been a while. I figured we'd do some, toying around with some tools rather than sit here and try to do some video that was way too technical. I know we did talk a month ago, 2 months ago, about the Snap-on thermal probes. We finally used it. One of the things that we did was we tested the temperature difference between a mixture to a pure substance to a mixture, which we have right here. If you can't see that, let me just get you down in nice close and pro. Okay. There it is. There's your graph. Down here we got ice. Put the probe in there, freeze it overnight, and we get nice and cool in the freezer. Then we put it on the stove and we heat it up, and that ice begins to rise in temperature. At this point, it is now up here. It is 0 degrees Celsius. As it climbs across, we go from 0 to 100 degrees Celsius, because 100 degrees Celsius is the boiling point. The problem is we have ice and water in here. So you don't get a temperature change in this flat spot. This is the temperature change. So as you notice, temperature's climbing, temperature flattens out. But why? Well, this is why. So I thought we'd prove the theory, and we'd set up this whole gangly operation to actually show you. And the issue is at this point you have, let's say, you got ice cubes, not the wrapper, and you got water. This right here, at this point, is going to be the ice, and this is the water. The reason why it comes from here, it's all ice, and then over here, it's ice plus water, and then over here, it's boiling, is because of the simple fact that at this point, every bit of heat that transfers in, it wants to go into equilibrium, which means that at this point, all the heat is being transferred to the coldest part. So it keeps going into the ice, into the ice, into the ice, into the ice. So every time this temperature wants to rise, it doesn't. Because every time it wants to rise, it goes whoop, right over into the ice until the ice is fully melted. So at this point right here, you're at complete and total water. So when it reaches this point, that's when it's going to go from 0°C, and it's going to climb all the way up to 100°C up in that corner over there. And that's what we're seeing in this book right here. What we're actually seeing is the ice melting at 0, 0, 0, 0, 0, 0, and then from here it's climbing again as it boils, or it starts to boil right around here. So actually we're at ice, ice, water, and then we climb, and that's how that works. I know I pretty much didn't read it the way they got it explained because the temperature scale is different, but that's pretty much the general gist of it. And I just thought we'd stick a probe in there and see if it was actually true. Now, let's keep in mind before we take a good look at the multimeter trend graph over here on the old Fluke 289 that this was not distilled water in a pure, sterile environment. So when we do the experiment, obviously it's a dirty environment. You're not going to get perfect results, but you will get the gist. This is the graph that we got. Now, as far as that little spike right there, where it's jumping all over the place, if you can see that pretty good, is I assume water got between the ice because the probe was stuck in the ice at the time. And then it finally went over, and then it climbed and climbed and climbed, hit its boiling point, and now it's boiling. That's a mixture of air and water. And as we said before, mixtures do not give off heat. Or it gives off heat, but it gives it to the other part. It's solid in that liquid form. But I assume that little spike in the graph right there was probably something along the lines of, I already set it up, where we had the probe in the water and ice, but the ice was right here. This is the probe, and then water was around it inside of the container. what I assume is this thing probably cracked on the side right there. And all this water probably seeped its way up in there. And the water obviously is warmer, so it gives it a jump in temperature as it makes that peak. But what you will notice is when it finally got to a boil, which is a more steady operation, you'll notice that it flatlined. We will scoot that all the way over, and you'll see that at that point we hit, what do we hit? 91.2. This thing's a little off. You gotta remember the probe is not made calibrated. We get into the middle of it, we're at 94. Keep going, keep going, keep going. We're still pretty close to that number. We don't really fluctuate a whole lot. Obviously there's impurities, there's a little bit of offsets, which obviously you can do an offset, because if the meter is not accurate, or you know for a fact that the probe is off by 4 degrees, you're going to offset your meter by 4. That way you get routinely the same result. And that's what we did. Did it work pretty good? Yeah, it's actually really responsive. I mean, I didn't really have an issue. And yes, I know some of you are looking at this thing thinking, in-size mag base. What a noob. Yes, I know, I should have got the Noga, whatever you call it, Casanoga. I should have used that one. I got the other mag base on the lathe right now, which also got to do a video about. As you can see, one popped up from a long time ago from a different page. It's still mine, it just happens to be migrated from a page I didn't take care of. So, one of the things we can do, okay, so we have our temperature all set up. Whew. There we go. Get that thing pointed out there. We got the probe tip, a grab. And it's actually pretty responsive, to tell you the truth. I mean, I personally like it. Another thing too, with these snap-on probes, yeah, these guys, woo, there we go. These guys right here, not durable at all. You saw me just take it right out of that mag base, right? Little tiny pinhole right there. It actually bent. See that little crease right there? There we go, a little bit of light. Yeah, right in here. That crease, I didn't even have that much pressure on it. It was almost nothing. I don't know if it was because I put this into the freezer and then took it out, put it near hot water, and expanded. I highly doubt it. It's stainless. If you're going to get these, my recommendation to you is stick with the name brand stuff like Fluke. I would get the Fluke probes. They're Inconel. These are stainless. They're pretty thin, and they're not very positively affixed. They're kind of, I don't know, kind of out there. They work, don't get me wrong, if you're doing basic testing, you're fine. But, I mean, these were $50 a piece, but I really wasn't too impressed. This is more for like the little shit. I mean, here's a number for it. You got it on the last video, we'll show you again. There you go. The EETH is the model number that the Snap-on represents with it, or recognizes with it. But, and they're alright. They're not precision tools, and stainless is kind of, well, it's a little weak. I'd rather have the Inconels from Fluke. They go all the way up to 1,400 degrees, I believe. This goes up to 750. And of course, those two numbers are Fahrenheit. But other than that, I just thought we'd get a quick look. A little fun video. That's pretty much it. This is Rob, Soundwave Specialties. I'm out of here. Peace.